Thank you very much, Rahul, for asking me to come here. I'm going to begin with kind of a tutorial for universe problem and what are the strategies for seeking solutions to universe problem. So, shine this so that everyone can see what's written. The light.
Similar to repeated lights, but the strength is better than what they refused, so hopefully.
Just be okay.
Can you move to the center?
Is the mic is the mic okay? Can you hear me at the end?
Can you move the board in the center?
So why inverse problems? They're inverse of something, and they're essentially inverse of what you might call direct problems. So what are direct problems? I'll just give you two examples. Here you have a gold deposit which is buried inside the earth, and you decide to find out as to where they are. In other words, you want to locate as to where this high density material is. Its density might change depending on its concentration. So you could represent it by rho of r dash, where r dash is the variable point. And because it's a high density material, you will make a gravity survey and measure the gravitational field at any point. Due to any particular concentration over here, the gravitational field will be, it's a simple example of Newton's law, r minus r dash square multiplied by g, and this is the volume. And if you want the whole thing, then of course it's over this entire volume. Now, this is something which we measure. This is our data. This is something which we desire, and that is our model, rho of r dash. So this is an inverse problem because given r dash, given rho at r dash, I can compute delta G to a very high accuracy, as accurate as Newton's law will allow me. But getting back is slightly different. I'll just give you another example, and that is, here is the satellite, and it's looking at radiation coming from the Earth at an angle which is theta, and the right is as cosine inverse mu. And the question is, this I, which this satellite measures at lambda and the look angle mu, can be calculated if I knew, for example, the temperature as a function of z. And I'll just show you how. The question is, the satellite is looking at all this radiation coming from the Earth, contributed by different layers, and we want to find out what T of z is, the profile, temperature profile. And this is a very simple exercise which we'll quickly do as an example. Imagine that there is a small thickness, small layer here called dz, and that length will then become dz upon mu. And what that layer is doing, that layer of atmosphere, is that it's absorbing part of the radiation that is coming. And we know what that is, will indicate its law. And it's also emitting, depending on what its temperature is. So the change in the intensity that this is contributing to is equal to that at incident over here, plus the black body, which is also dependent. So that's a simple thing, and that allows us to calculate I. For example, if I subsume that into the variable delta tau over here, then di over d tau can read it on this side. I beg your pardon. It's already over here. And the best way to integrate is just to multiply by e to t. And this can immediately, you can see, you can write it down as I integrated from the surface to the top is this. And you can see little reflection will show that when you put these limits at the top, you'll get, and this is what the satellite will see, lambda mu. And on this side will be I0, and this e to t tau over mu can come on that side. So it really becomes so again, and of course, that will turn to zero because most of the energy that comes from most of the incident radiation that emanates from here gets eventually lost by the time it reaches the atmosphere. So what you will get is just that, and again you'll be able to see that what you measure, and this is your data, is a function of Bz, B at Z, and if you know Bz at lambda, then of course you'll be able to find out what T is. So that is how T is related to what you measure, except that it happens to be an integral sign. These integrals are known as the Fredholm's integral for the first time. Now, in some cases you'll remember that these are invertible. You can write, for example, f of t here as a Fourier integral, and inside you have the Fourier transform, which is capital F omega. And you can invert it and write f omega directly in terms of f into f of t. But such situations are not normally available to us. There are a few transforms which are invertible, but very seldom. Further, we would not be able to do that for one reason, that data is always discrete. And therefore to integrate it, even if you are able to take it in the integral, it will be very difficult. So what do? We discretize it. And when you discretize it, I'm going to rub all this off because this will just to show you how an inverse problem is set. So here we have a condition, and this condition could be T of Z, temperature profile, temperature variation of the atmosphere above the Earth, and here you have some data. Or you could have the treasure I showed here, and you have the gravitational field. You could have something else. You could have a big explosion over here, and you could be measuring something on the other side, a very tiny explosion, and you could measure something across this side. This could be a small medium, like a big block of wood or a big block of concrete, which you want to find out what its properties are, or it could be the whole Earth. So the scale could be very large, but the whole idea is that given this, given the distribution of rho r, given the distribution of Bz, which we'll call model for the sake of getting some number, I'm just calling it model, which is m, and this is my t. And this theory takes me to this. The question that we are asking is, we have to go from data to here. Can I design this path in such a manner so that I can go from data? I'll have to find out a function which is in some way inverse of this function. And what is it? And is it possible, if I call it the inverse, that it will actually take me to this place? So those are the questions which are partly philosophical, partly computational. But Hadamard, I forget when he was, but he wrote 4 conditions that well-posed problems must satisfy. And these 4 conditions were, I won't write them, existence. The solution must exist. Questions which physicists never bother to answer. They just assume that the solution exists. But I'll give you an example. If there's a buried deposit of iron, which is magnetized in a certain direction, and if you measure the magnetic field, both in magnitude and direction, you can compute as to where that buried magnetic deposit is. But if we only give the magnitude and not the direction, this solution doesn't exist. So there are questions where the solution itself does not exist. And then of course, the question is not well posed. The second is the solution unique? So we'll take examples here and see as to whether the solution of the inverse problem is unique or not. And it turns out that in most cases it is not unique. The third condition is of stability, which means that if the initial conditions are slightly perturbed, would the final solution also perturb slightly, or would it diverge very substantially? In other words, is there sensitivity to initial conditions, or would small perturbations lead to very large? And the fourth one, he said, was constructibility, that one should be able to write down an algorithm which will take you from data to whatever you are seeing. So these four conditions he put forward as conditions required for well-posedness of a question, and problems which do not satisfy this are called ill-posed. Mathematicians turn their back on ill-posed problems for a very, very long time until satellites appeared on the scene and questions like that began to be answered. Incidentally, the kind of approach that I have shown here can be used to answer answers to various questions. What is the ozone distribution in the atmosphere? What is the aerosol distribution? And so on and so forth. So, but the approach is going to be very similar to physics slightly. So, the question is that how do we pose this problem? All these, I could write d as some function of, and that represents my theory, as well as the arguments of whatever the arguments are, arguments of the experiment. Where I do the experiment, what are the frequencies I make measurement, or wavelength, and where. All those are subsumed here. And this could be nonlinear. And if it is nonlinear, you can always linearize it about some n equal to n0. And in that case, you can see that you can write this, for example, as g grad g m minus n0. Something like that, and that is d0, and that is your mu d dash and m dash, then I can write this as d dash and dash. So the crux of the whole thing is that I can write down my direct problem, as I said, in distinction to the inverse problem as gm equal to d. And the exercise that one wishes to carry out is that given d and given g, find out. So one strategy could immediately be that I ask the question, what is that n which is going to bring, which when operated by g is going to be as close to d as possible? In other words, somehow minimize some norm of that. And one usually chooses the L2 norm. I shan't go into it why, but one can in principle choose LP norm by any particular p, depending on how your data. For example, the higher norm you take, the more weighted you are putting on data which deviate from any particular regularity. So one can minimize that and ask what is that g, or what is that n, which is going to give me this ability.
So are you assuming it's deterministic always, or is it
I am at the moment assuming that this is deterministic, and this is my g, that's n. The way it is written, you can always reduce it to probabilistic form. You can always reduce it in the same form which Professor Sepia showed yesterday evening, so that because of the symmetry between D and M or data and model, which I shall do at the end of this talk or tomorrow. So this is a matrix form. This could be my n cross m, n cross 1, and the observations are n. Well, yeah. If m is equal to n, then you know that you will probably say I've got the solution, because this is a square matrix. M is equal to n. This will be a square matrix. And I could always write E equal to G inverse of N. And every graduate student knows how to find out G inverse of a square non-singular matrix. So you got a perfect solution. I was remiss in writing this equation like this. There is a very important quantity which I have missed, and I missed it deliberately because I wanted to add it now. If there is anything that you measure, there is inevitably an error. And if m is equal to n, you are going to get an exact solution, error notwithstanding, which means that you will get a unique solution. You also look upon
m equal to G inverse D.
This equation, in m equal to G inverse D, that's the equation.
this one.
Yeah.
I beg your pardon. I'm so sorry. Thanks, Harry. I'll be making a lot of arithmetical mistakes, by the way. So remember that even if it was a square matrix, non-singular, we'll get a unique solution, but not necessarily correct, because we would not even suspect that there was error in it. And therefore the question is, would you ever get a unique solution? The answer is no. If n is not equal to n, greater than n or lesser than n, then we run in another problem. The solution is necessarily non-unique. So Hadamard's second condition is never satisfied in any inverse problem. So n is greater than, let's say n is greater than n, or we have explored this, n is equal to 1, and 2 is n is greater than n. And here you have more number of data than you have number of models. You can say, Pura, that's a wonderful situation that we are in. And you see that in that case, if you look at this equation, Gm is equal to D. That means this D can never really be fitted in the column space of D. And there are always a problem as to what is it that is missing. What part of D is missing, it cannot be accommodated. However, you can always get a unique solution if you impose some conditions on it. And one of those conditions could be this. The moment you put this condition, this is going to give you a unique solution for m. And that does not mean that it is a correct solution, but it is a unique solution. And in that case, you at least beat the problem of errors, because you will find that this is an inconsistent set of equations, simply because the errors here which are going to be random, and therefore even if there are larger number of equations than the number of unknowns, they are going to be inconsistent, and you will at least become aware of the fact that there are errors to be taken care of, which one would not be aware in the case of n equal to m, and you will get a unique solution. Here also you will get a unique solution subject to that condition. What happens if we have n which is less than n? Number of data points. This is the case when you have a set of simultaneous equations where the number of equations are less than number of unknowns, and you know that there is no unique solution. There are in fact a large number of solutions. But it's still in the real world that we live in, the inverse problem one is concerned with must yield a solution, so we must impose some criteria on it. So here we impose the criteria of this, for short I'll call it least square. Can we think of a criteria here? And one of the criteria one thinks of, although it has no logical basis, and indeed there is no logical basis for putting least squares. We often think that there is something logically perfect about choosing that norm, but there isn't. Except one.
There is.
Except one.
If you have a square that are lots, that is the optimum. That is the estimate.
Yeah, the optimum is a word.
No.
There was a noise model, right? If you assume it's a classic
Yeah.
noise model, then that
There is just one justification for that if your noise happens to be Gaussian distributed, then you can also show that that condition alone is going to give you exactly the same model value as this will give. And so indirectly one can say that therefore I have a justification.
There are two arguments when you have a Gaussian distribution. Whether you use maximum likelihood or least squares. Bayesian methods, you get the same answer.
You do. And there is something else which will also give you the same. And so there are these strategies one can use to find out as to what is the proper G inverse. There are other strategies too, and I'm going to just take one of these examples. Yes.
So maybe one remark. So people like Devinder and I would probably say that the conditions are even a little more general. Namely, if the only information you have about the errors is their variance, then the maximum entropy distribution conditioned on that knowledge is a Gaussian, and then the appropriate solution would also be to minimize the square deviation.
Right. There are all those words, but they are words with lots of ifs
I
and
think
buts.
you're always worse.
Yes. No, when I said that it is not logically perfect, I said by itself it is not logically perfect, unless you import in some other condition. So I'm going now.
Can you discuss the case 3? Because I'm interested in that. The third case, where n is less than n.
Yeah.
You were
So
going to-
when n is less than n, one says, well, what kind of condition will I put in? And there is again a logically imperfect solution, not solution, answer, and that is that I will seek a solution which minimizes the norm of m. That means if m is, remember, a column vector like m1, m2, m3, the square of the sum of the squares of these is minimum. It will make physical sense if this is some kind of an energy, for example, where in a system energy is minimized to
The reason I
possibly.
raise the question is that a question largely discussed by statisticians, where you have the problem of large p, small n, many
Yeah.
parameters,
Yeah.
small n. That's exactly the problem which pops up in physics
Yeah,
in the lattice QCD equation.
yeah.
That's exactly what happens. And of course, you could solve them in different ways, and you are absolutely correct. There is no logically soundproof way to solve it. You make assumptions and you produce an answer.
But I'm going to take a slightly different approach now. I'm moving on from my focus on the model to focus on G. The G vector itself is conditioned by experiment alone and theory, and not by the data. Let's look at it. This Gm is equal to D. Supposing that I have, by some means, found out an inverse G inverse, I'll call it, which multiplied by data gives me something close to M. It won't be exactly M. We have agreed that there are no unique solutions, so I'll call it M hat. It's an estimate of M. Now, look at this. I multiplied this by G, and I multiplied this by G, and this gives me G hat. Right? And supposing I call N, then MD is equal to G hat. That means I can resolve my data if my N is equal to identity matrix. In general, it would not be. So the question I could ask is, how close it is to the identity matrix? And can I in seeking my proper D inverse, can I use that condition that its departure from the identity matrix, row by row, should be as small as possible? And I'm going to do that right here on the board. So let's try to do that, if it is clear. One could have asked similarly a question about the model, how this is exactly asking how well the data is resolved. One could ask how well the model is resolved. And for that, what I could do is multiply this by, I hope I didn't make a mistake. Okay, let me write G minus T, I T multiply here. T minus Gm.
So why is it G minus G instead of G minus 1?
The exponent for G, the inverse of G.
I'm just calling it G minus D because somewhere at the back of my mind, that I have not explicitly said, is that it's a generalized inverse. So I'm calling it G minus D rather than D minus 1.
SVD line.
Okay, okay. So if I P multiply by this, I get this, and that is different from that one. I'll call it R. And R is telling me how well my model is resolved. If R is identity matrix, then M is equal to M hat, and I resolve my model completely. If not, then the good question to ask will be how close it is to identity. So one could see those conditions. One could say, give me that G minus G, which is going to reduce I minus this. Or I can ask, give me that G minus G, which is going to reduce I minus this. I'm just going to do one of these and leave the other for some of the questing minds here to do on their own. So let me say that here is my cost function, which is I wish to minimize the least square norm. That means the departure from identity of this data resolution matrix. Now, please tell me when it is 5 minutes left before I do that. So
15 minutes.
okay. Now, n was equal to, I keep forgetting, G minus D. Forgive my so that's my JK. I differentiate it with respect to that's going to give me 0, and I'll first take all these as constant. And that will give me delta NQ, delta IR, plus I'll now take that one as constant.
So, I'm a bit confused. Where's the data? Is there no
Beg
data?
pardon?
Where's the data? There's no data? In this equation, is there any?
I started by saying
Yeah.
I'm shifting the focus from model and data to the G inverse itself. So, because G is not dependent on data. G is only dependent on the conditions of data, not on the data itself. So there is no data.
You want to just find the inverse of G.
Just give me a minute. So, okay, I is equal to Q, L is equal to Q, so that becomes G, K, Q. G, K, P. I is R. And if you look at this, this is going to give me something very similar, except that P is the dummy of it. So if you don't mind, I'll just put it this equal to minus, because that's going to give me exactly something similar. KQ. And this I equate to 0. And that's going to be my, I take the transpose of this, so I can write it as GT and that's exactly what you would have got if you have minimized dm minus t whole square, the least square. So, if you like this angle justification for the least square inverse, a very oblique one. If, on the other hand, I had minimized R here, it was our model resolution matrix, I would have got a minimum norm inverse.
But let me try and understand where you're going. And pardon me if I'm
Please?
not keeping up with you.
Yeah.
Are you giving an alternate justification for the least square?
No.
Or are you
I
addressing
did
the problem?
want to get one least square solution in this short period.
Okay, you got it.
One of the many ones, one of the several ones. Right? And I'm just going to ask you as an article of faith to trust me that this is exactly the same what you would have obtained if you had used the least square.
Exactly.
And
G
then-
transpose G inverse.
And then
Exactly.
I'm not going to do any more calculation. What I'm going to show you, what I'm going to assert is that if I had minimized R, which was my model resolution, I would have got something which is, I don't remember this in my head, but that minimum norm solution for the inverse is something which I would have got.
And just to get my bearings,
Yeah.
what was the key idea here behind getting this estimate? Or behind getting this result?
The key idea here is that I haven't got the data, but I have an experiment in mind. And the condition of my experiment, in which some of the variables will be at my control, allow me to test as to how good this D inverse is going to be in experiment design. Also, if I want to ask what is the kind of model I'm going to get out of this application of this D inverse, because my model estimate is going to be okay. This is my D inverse. This is my model estimate. So I've got my model. I want to know how good my model is. So in other words, I want to know my covariance. And that's my covariance. So I can ask the question, how good is my model? What is covariance? Not only the solution, but the quality of the solution. This, of course, I can ask in each instance that I find a D inverse.
Now,
Yeah.
So there is this kind of analysis, unless I'm totally misunderstanding you, I think it's used in lots of applications, often goes under the name of things like ridge regression, where you assume a linear mapping from your model parameters to your data with Gaussian noise, and you assume some Gaussian prior on your model parameters, and then the solution is just the SVD matrix.
Well, the solution, the ridge regression solution, is slightly different. It's a combination of these two extremes that I'm taking care
So
of.
by just tuning the weights on the
Right.
two, you can get
Right.
somewhere between those two.
So
solutions.
often the situation, the problem situation is visualized as consisting of a mixture of both these conditions. That part of the model is overdetermined and part is underdetermined. And therefore you say, well, I'll minimize n and I'll minimize some fraction of r together. And then I'll get a combination of both. But that's a matter of detail, and that's not the only one. I could ask, for example, I don't only wish to minimize n or r or least squares. I also want to minimize the covariance, right? So it depends on how I constitute my cost function. There are tens of ways of constituting different kinds of cost function, depending on how you prescribe it. So since it's only 5 minutes, I'm not going to do something else that I was going to do, and it's called a singular value decomposition, which allows you to separate, for example, the Cn equal to D, sorry, it's also, remember that Gm equal, any solution of Gm equal to 0 is also a solution of that. And when n is much less than m, then there's a large part of the model space is something which is not reflected in the data form. That is known as the null space of this particular one. And if we want to find out as to where is my null space, where all my uncertainties lie, then the way to go is singular value decomposition. But what I'm going to do, because of shortage of time, is now to come back to pose the same problem in the way Professor Sevier posed yesterday, and write it as probability that I have a model that will fit the data is equal to and if I maximize that probability, then I'll get a J inverse, which is Bayes. So maybe I'll do that tomorrow. But what I wish to do now is to show you quickly some results which we obtained using earthquake-generated shock waves which travel large distances over the Earth to see as to what they are undercarried beneath the Indian subcontinent. So I'm looking at Rayleigh waves, and Rayleigh waves are the waves which are confined to small region of the surface. This is the Indian subcontinent, and do we have a fun here? And geologists tell us that it is made up of a large number of cratons which are of different ages, and they came together, but they came together long time ago, about 3,000 million years ago. They came together and formed this Indian landmass, and about 50 million years ago, the Indian landmass started moving towards, well, it started moving about more than 100 million years, but 50 million years ago, it collided with the southern front of Asia and raised these mountains. So what does the undercarriage look like? Physicists like me have to translate this question into how do I characterize the coefficient of rigidity, for example, or the strength of the material that we do. So what we did was that these are all our seismographs. We combined the data with our colleagues in Cambridge who went through these seismographs over here, and these are our own. And we looked at earthquakes over here, and the paths between earthquakes, all these earthquakes, and all these seismographs. So you can see those, and those are the waves we are looking at. These are the Rayleigh waves. Those are the paths that cover the whole of India is virtually covered completely by these paths, so you can see that. So what these paths are, that along each of these paths at different levels, I have the average velocity. And I now want to find out as to what is velocity in different segments. So that shows how Rayleigh waves travel in the Earth, and their various modes, and those various modes give me sensitivity to various depths. So I am able to segregate this. That's our test. So at a depth of about this is 10 seconds period of the wave, which is close to about 12 kilometers or so. This is what the continent looks like. The materials are soft here, not soft, but much less compact than in the interior over here. And this is a map which is produced by Glasscare Masters, showing all the sedimentary basins. Sedimentary basins are those regions of the earth where the material density and elastic constants are much lower. So one can see that there is one-to-one correspondence, because what I am going to show you at deeper depths will not be so easily corroborated, but here it is corroborated. And that, for example, is along those. Sorry, one of these got white, but doesn't matter. As you go from South India to across the Himalayas, and these are the mountains, this is what the earth looks like at various depths. And all this has come out through the kind of analysis that I did. Thank you very much. Questions?
What do you have a way of getting G inverse, generalized inverse,
Yeah.
without reference to the data? And now you get the data and apply the
But
generalized.
you have the conditions of the experiment.
Okay.
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 G is not dependent on data, and therefore it comes as no surprise that G inverse will be dependent on data. But G inverse but both G and G inverse are dependent on the conditions of experiment. What are the frequencies at which you make measurements? What are the space-time
Experimental design.
experiment design?
Okay. So the next experiment you do, the data you see now will be incorporated somehow.
Beg your pardon?
The next time you do an experiment, you'll have a different G or for each experiment.
So you can design your experiment that your G inverse or G inverse G are as close to identity as possible. So there is a possibility there for doing experiment design in advance of going in the field, and this is particularly true when people do it. Petroleum geologists, for example, who look for petroleum reservoirs. They spend millions of pounds or dollars finding out where it is. And they do all this in advance, before going and carrying out their experiment. Because this is far cheaper than actually carrying out. Essentially asking where does the information reside in the best possible manner.
All right, if there are no more questions, we'll thank Mr. Gaur. So, around for now, we're meeting here back again.
One sec. We had planned, yeah, so we're officially over, but there was a lot of popular interest in Moser continuing. So the idea was that he will speak for a little bit now, and due to popular demand, we'll for after 15-20 minutes. And those who need to leave now can do so, of course. But, yeah, so. And is there any announcement before we start? No. So those who are interested, come back here.